Right now, sitting still, you are moving at the speed of light. You, perfectly at rest, are traveling at roughly 300 million meters every second. The reason that sounds wrong is that we've been taught to picture time as a river flowing past us, and space as the stage we move across. Physics says something stranger. Time and space are the same thing, and everything in the universe is already moving through it at one fixed speed. The only question is how you spend that speed.
Here is what that means. In Einstein's relativity, you don't move through space and time separately. You move through a single four-dimensional thing called spacetime, and the total speed of that motion is always exactly the speed of light. When you sit perfectly still, none of your motion goes into moving through space, so all of it goes into moving through time. You age at the maximum possible rate.
The moment you start walking, driving, orbiting the Earth, a small slice of your motion gets diverted from the time direction into the space direction. You don't speed up overall, you just trade a little future for a little distance. That trade is time dilation, and it is not a theory you file away. It is why the clocks on GPS satellites tick a fraction faster than clocks on the ground, and engineers have to correct for it, or your phone would send you to the wrong street. So the first speed limit of time is this. There is a maximum rate at which you can move into the future, and you are hitting it right now. But that is only the beginning of the story, because a harder question sits underneath it.
Not how fast can we move through time, but how fast can time itself change? Imagine the universe as a stopwatch. How quickly can it flip from one state to the next? Can change happen instantly? Quantum mechanics says no. A physical system, whether it is an atom or a computer, cannot jump from one distinguishable state to another in zero time.
There is a minimum interval for every transition, set by how much energy the system has. Push more energy in, and the system can tick faster. This is the quantum speed limit, and it applies to everything. A single atom, a brain, a star, a civilization. Follow that thread, and it gets uncomfortable. If energy makes a system tick faster, then a faster computer needs more energy. Hans Joachim Bremermann worked out the ceiling for ordinary matter. No lump of atoms, no matter how cleverly arranged, can process more than about 10 quadrillion bits per second per kilogram. Seth Lloyd later asked the extreme version. Take exactly 1 kilogram, squeeze it into 1 liter, run it at the absolute edge of physical law. That ultimate laptop tops out near 10 to the 51st operations every second. Fast, but not infinite.
Because what do you do if you want to go even faster? You add more energy. You pack more mass into the same space to raise the clock rate. But there is a point where packing in more energy stops helping and starts ending things. Compress enough mass into a small enough volume and you cross the Schwarzschild radius. You have built a black hole. The very attempt to make a faster clock destroys the clock and hides it behind an event horizon. When you combine gravity, quantum mechanics, and relativity into one limit, the maximum tick rate of nature is no longer about how much stuff you gathered. It is fixed by the Planck time.
The smallest meaningful interval in physics, about 10 to the minus 43rd of a second. Nothing local can ever happen faster than roughly 5 times 10 to the 43rd ticks per second. That is the frame rate of reality, and it cannot be beaten. Now, a speed limit this deep should show up everywhere, not just in computers. Physicists noticed a problem. If there really is a smallest possible slice of time, then standard relativity has a glitch. Under ordinary Lorentz transformations, an observer moving near the speed of light would stretch or shrink that tiny interval, measuring a time shorter than the minimum. That breaks the rule that the laws of physics are the same for everyone. To fix it, researchers like Giovanni Amelino Camiglia
Joao Magejo and Lee Smolin proposed doubly special relativity. It keeps the speed of light as one universal constant and adds a second one, the Planck scale itself. Length, time, and energy all have a floor that no observer can measure away. The wild consequence is that at the smallest scales, time may not flow at all. It may come in steps, like a movie projected frame by frame, except the frames are separated by 10 to the minus 43rd of a second. Worse, under this picture, light itself can travel at slightly different speeds depending on its energy, because space is no longer perfectly smooth down there. Astronomers have tried to catch this by watching high-energy gamma rays arrive from distant explosions. If the effect is real, the most energetic photons should lag behind the others. The data so far has not confirmed it, but the fact that we can even test whether time is grainy tells you how serious this idea has become. The limit does more than describe reality. It appears to protect it. Apply an upper bound on how fast anything can change to the early universe, and one of cosmology's ugliest problems disappears.
In standard general relativity, if you run the expansion of the cosmos backward, everything collapses to a point of infinite density, a singularity where the equations blow up and time itself begins. But loop quantum cosmology, which builds in those quantum gravity bounds, replaces the point with a repulsive force. As a contracting universe squeezes toward the Planck density, the math refuses to let it hit zero. It bounces. The Big Bang stops being a beginning and becomes a transition, a moment the universe turned itself inside out and started expanding again. Before that bounce, there was a before. Thermodynamics tells a similar story. Black holes are the universe's ultimate entropy machines, and as they evaporate through Hawking radiation, the emission rate would, in the naive math, race toward an infinite explosion at the end. The quantum gravity cap stops that too. It sets a hard ceiling on how fast entropy, heat, power, force, and even temperature can be pushed. No thermal runaway, no instant dissipation. The universe is forced to relax on a schedule it cannot break, which is part of why stars form, engines cool, and the cosmos does not simply flash out. Then comes the turn that undoes the whole picture. What if time is not a thing that flows at all, but a thing that appears? In the Page-Wootters formulation of quantum gravity, the total state of the universe is completely static. It does not evolve. Time does not tick anywhere in the big description.
What we experience as time emerges only because one part of the universe, a clock, becomes entangled with another part, a system. You read the clock, and relative to its reading, the system looks like it is changing. That is the only time there is. And if there is a maximum rate at which that clock can tick, then there is a maximum size and resolution that any clock, and therefore any experience of time, can ever have. Push the system and the clock to interact faster than the universe's ceiling, and the clock stops behaving like a clock. Time, as a clean, flowing thing, falls apart. So here is where the story lands. You began by learning that you are already moving at the speed of light, trading distance for future with every step. Then the deeper rule appeared. The universe has a fastest possible tick, set by the Planck time, and no black hole, no computer, no civilization can ever exceed it. That single limit suggests time may be made of indivisible frames, that the Big Bang may have been a bounce from something earlier, and that time itself might be an emergent property of a clock we happen to be entangled with. Every event you will ever live through is paced by a beat no one can outrun. The strange part is not that the beat exists, it is that without it, there might not be a story to tell at all.